stress strain curve is. Right? And then over here, back to the diagram. The distance from here to here is L1. Okay. So we know that over here, we have a delta L. Delta L is equal to L1 minus by L0. And we know that over here, we have an area. Okay. Area going to call it AS. And we know that the stress in Y is equal to minus PY divided by what? AS. So what we are going to get on a stress strain curve that you don't normally see, but it should be seen done this way, is your stress strain curve will go in a what? Negative direction. Why? Because over here, strain is equal to what? Negative. Stress Y is also equal to what? Negative. Agree, disagree? Yes. Yeah. AS. AS is the cross-sectional area. Okay. So you don't see a lot of this type of graph because what people tend to do is just tend to draw what? Positive. Are we clear? Okay, so what? So we know that this over here is our what? Young's modulus. But what we tend to see is people will tend to, okay, we're also going to stretch this line out and this is what it's going to be. But everything has to be negative because the strain we have is what? And so to calculate strain, I'll let you guys copy this first. I'm going to use a new page. Okay, we'll copy this whole thing. Right? So from here, I'm going to write out a few equations for you to have a close look. So we know that delta L is equal to L1 minus L0. And under compression, we know that L1 is going to be what? Smaller than L0. Okay. So therefore, delta L is always going to be equal to what? Negative. So when we calculate our strain in the y-axis, we have L1 minus L0 divided by L0. So this will be equal to minus delta L over L0. Okay. So I will address this as my equation number 1. To calculate stress Y will be equal to minus EY over A. This is our equation number 2. Then we are going to apply Hooke's law. Okay. And we're going to substitute, or not apply, we're going to substitute equations 1 and 2 into Hooke's law. Hooke's law states that stress Y is equal to Young's modulus multiplied epsilon Y, where E is our Young's modulus. And very fundamentally, what is the Young's modulus for steel in megapascal? Anyone? How many? So 210 gigapascal. Young's modulus of brass. Anyone? I said question for Tesla. Those student, it's a technical question. And this is one of the questions I said. Those students that want to become design engineer in Tesla has to know this. Okay, they pay me a lot of money to design 10 questions for manufacturing and for structure analysis. And this is one of the questions. What's the other modulus of steel, of aluminum? Anyone? Huh? Aluminum, sorry, for brass is 110 gigapascal, and for steel is 70 gigapascal. Are we clear? Okay. Just remember this number. It's not that difficult. You can remember your girlfriend and boyfriend phone number. Yes or no? This number is very important. Are we clear? So from here, we have what? Stress Y is equal to minus PY divided by A. And this is equal to Young's modulus, and epsilon Y is equal to what? Minus delta L over L naught. Okay. So from here, we know that delta L is equal to Py L naught divided by AE. Okay, so this is our equation number 3. Seen this before? Yes or no? Right? This is the same as, so delta L is also known as the what? Axial deflection. Okay, it's also known as the axial deflection. Okay. Now, unfortunately, this formula is useless to determine when buckling will occur. Right? Some of you might say, why is it useless? Okay. Cross-sectional area did change, right? Length is still the same, but it does not consider is useless for buckling. Any idea? Any idea why? Yeah. Well done. The answer given is in buckling. What is the deformation shape? Can you see this? What does it look like? A curved feature, right? So can you see how my hand is pushing down axially? Yes or no? This formula you see on the board, the deflection is what? It has to be axially going in. Are we clear? Okay, that's why this formula is useless for what? For buckling. Okay, now another question. What sort of loading condition will give you a deflection like looking like this? Yes. Okay. Eccentric loading. What sort of eccentric loading? You're partly right. What sort of deformation, what sort of loading can give you deformation like this? That's not axial. If I were to turn this around, and if I were to push my left hand and right hand upwards, what deformation pattern do you see? Yes. So can you see, if I push my finger left and right upwards, what's the sort of deformation I get? You get a smiling face or sad face. If I put my structure this way, and if I press it down, isn't the deformation pattern the same? Are we clear? So how do we analyze buckling? Using bending moment equations. Yeah, is that freaking interesting? Then you guys will ask me, Eugene, where did this pi squared come in? Yes or no? Okay, so let me finish off. Okay, let me finish off. So we know that this equation is useless for buckling, right? Is because the deformation is only in the what? Axial direction. Okay, because the deformation is now. Before I go further to elaborate more on buckling, is what is stiffness? Remember, we are still coming back to this problem. What is stiffness in structure analysis? Remember, we started like, oh, this is not stiff enough. This is stiff enough, right? So how do we analyze stiffness? And this is where I have to define stiffness. And I taught this before in 2Q first week. The unit or the symbol is small k, and the unit is what? Newton per what? Meter. Now, stiffness usually has to do with a what? Spring. Okay, has to do with a spring. And then if we were to compress it, the spring gets smaller, and this is your Py. Okay. So therefore, K is equal to Py divided by our delta y. Okay, so this distance over here, this is known as our delta y. Okay. So this is where the units is Newton per meter. So we know that Py is equal to what? It's equal to K delta y, right? So we know that delta y, from our previous equation, we know what is our delta y, right? So from this equation over here, or not over here. So where am I now? I'm lost now. So from here, our delta L is also equal to our what? Our delta y. Okay, so I'm going to rearrange this. So Py over K is equal to our delta y. And delta y, for this case, is also equal to our delta L. And this will be equal to Py L naught over AE. We can get rid of our Py's. Okay, so the stiffness K, so therefore, the stiffness of any structure is equal to AE over what? L naught. Again, this stiffness, definition of stiffness cannot be used for what? Buckling. Okay, this stiffness cannot be used for buckling. Okay, so in order to use for buckling, we have to reformulate reformulate, okay, our analysis. So we are going to look at the deformation pattern. For buckling. Okay, we're going to look. So for buckling, now I have a structure over here and the structure have, okay, so this is our structure and this is our L0 now. And then we have a load over here, P, and P is our axial load. Transformation X and Y, rotation about Z. And then we have at this point, or what we have over here is A, and A is our cross sectional area. Okay. Now, before I let you go, any of you been to Hong Kong before? Those who have been to Hong Kong before, can you put up your hand? None. Some of you have been to Hong Kong before. Now, in the world of structure analysis, Hong Kong is the best in designing structure that can withstand buckling. Any idea why? If you go to Hong Kong, the building is yay narrow and too tall. Are we clear? Okay, so just Google landscaping in Hong Kong. You'll see for yourself. Okay, I'll see you guys. Is it tomorrow? I'll see you guys tomorrow.
I have a question. What's the difference between second moment of area and area moment of inertia?
One is mass dependent, the other one is not.
Oh, so the area moment of inertia, that's
math, right?
mass dependent. And the second, like second moment.
So how do test the stiffness of the paper?
Huh?
How do how to compress the paper without
You need test in tensile.
what?
You need can test in tensile. Tension.
Okay.
You cannot test in compression.
I think I can. I can test it in a lot of paper.
Yeah, but usually they do tension there. Okay. Good question.
So again, is there any material that has different tension and compression?
All materials are
Same or different?
different. All materials are different in tension and compression.
Yeah. So yours modulus are same or different for tension and compression?
Gas models are similar, but the yield is different.
It's you.
Yield strength. Okay. Okay. Yes.
How can you predict if it's going downward? How can you predict which way it's gonna like?
We are not predicting directions.
Okay.
We're predicting when.
Okay.
I can't predict, but we
I was
know the
gonna say,
shape.
yeah.
We know the shape. That's a good question. Okay, but we know the shape. Okay. Yes.
Just because I couldn't, I will not be able to do the test on the 6th.
Can you do it earlier?
Yeah, I think so.
Yeah. So I will schedule you earlier. Send me